Good morning, dear students. The course name is Process Control, and myself, Dr.N.JAYA, Professor in the Department of E&I Engineering, ANNAMALAI University. Already we discussed lecture 1 in the last class. While discussing the lecture 1, I told you about the type of control action needed for this example. What is this example? This example I shown in the last class, right? So what is this example is, this is a flow control loop. We are going to measure the flow using this flow transmitter. The output of the transmitter is given to a flow controller. The flow controller will actuate this control valve. What is our primary objective? Our primary objective is to control the flow of the process stream. By manipulating this control valve. Now, I told you in the last class what is mean by direct acting controller and what is mean by reverse acting controller and all. Most of the flow transmitters, coming to the flow transmitter, most of the flow transmitters are always a direct acting, in the sense that the flow rate, when the flow rate increases, the transmitter output will increase. Then coming to the valve, I already told you in the last class, there are two types of valves available. One is called as air to open valve and other one is called as air to close valve. Air to open valve and other one is called as air to close valve. You know the difference between air to open and air to close valve. What is mean by air to close valve? When the supply pressure is increased from 3 to 15 psi, the valve gets closed. What about the air to open valve? When the supply pressure is decreased from 3 to 15 psi, the valve gets closed, right? So, and similarly, I told you about this flow controller. There are two types of controllers are available. Two types of control actions are available. One is called as a direct acting controller and another one is called as inverse acting controller. Now, let us assume that the flow controller is a direct acting one and the valve is designated as air to open. What is the meaning of air to open? More air, more open. More air, more open. More air, more open. That is called as air to open valve. More air, more open. Okay. Coming to the controller. What type of control action needed for this example? Remember, the flow transmitter is a direct acting one. Valve is a air to open valve. What is the meaning of air to open valve? More air, more open. That is, at 3 psi, the valve is fully closed, right? Fully closed. Whereas at 15 psi, the valve is fully open. Fully open. Now, you just think about it. What should be the type of control action? Whether it should be a direct acting one or inverse acting one. And just recalling what is mean by inverse acting and what is mean by direct acting controller. This is 4 milliampere and this is 20 milliampere, right? So, this one is called as your inverse acting controller. That is when Kc is greater than 0, or in other words you can say that positive gain controller, right? The other one is called as a direct acting controller. Now, in this case, suppose if the process variable is above the set point. Let us assume that the process variable is above the set point. This is your set point, right? And this is your process variable. When the process variable is above the set point, what happens? We have to reduce the controller output by closing a valve a little bit, right? We have to reduce the controller output by closing a valve a bit because the process variable is exceeding the set point, right? So, in this case, so what happens to the controller output? when the process variable increases, we have to reduce the controller output. That is, when process variable increases, controller output decreases. Increase decrease action, or in other words, decrease increase action, both are called as inverse acting controller. So as far as this flow control loop is concerned, we have to use the inverse acting controller or reverse acting controller. Incorrect choice, because the problem is, if you choose incorrect choice, the incorrect choice will result a loss of control, right? I hope now you understood what is the difference between a direct acting controller and the inverse acting controller, and when we have to use a direct acting controller and when we have to use the inverse acting controller. So as far as this flow control example is concerned, we have to use, no doubt we have to use a inverse acting controller when the valve is a air to open valve. Similarly, you just think about the other case. Suppose if the valve is a air to close valve. What is the meaning of air to close valve? When the supply pressure is increased from 3 to 15 psi, the valve gets closed. That is, at 3 psi, the valve is fully open, whereas at 15 psi, the valve is fully closed. So in this case, suppose if the process variable is above the set point, in that case what you have to do is, you have to increase the controller output. So what happens when the process variable increases, controller output also increases, right? So in that case we have to use the direct acting controller. No doubt we have to use a direct acting controller if the valve is a air to close one, right? Now you clearly understand. I hope now you clearly understood the difference between a direct acting and inverse acting controller. Depending upon the action of the control valve, we have to choose whether we have to use a direct acting controller or inverse acting controller. Okay, now we are going to discuss about the lecture number 2. In lecture 2, we are going to discuss about first the mathematical modeling of a process, right? Before enter into the mathematical modeling, first we must know what is the need for mathematical modeling, why we need mathematical modeling basically, right? You just see this diagram. This diagram shows a processing system, right? Processing system or a plant which contains the input variables as well as output variables. In the input variables, again there are two different variables. One set of variables are called as manipulated variables, and these set of variables are called as disturbance variables. Both are considered as the input variables. Then coming to the output, these are the output variables. Again, the output variables are classified into two categories. One set of variables are called as measured outputs, and other set of variables are called as unmeasured outputs. What is the meaning of measured outputs? By using a sensor or transducer, you can measure these output variables or the process variable, and whereas these variables cannot be measured by using a sensor or a transducer. That's what they are called as a unmeasured output. I hope you are already aware of what is mean by manipulated variable and process variable and all. These variables already we discussed in lecture 1. Once again I am recalling the variables. Manipulated variables means what? Variables which cannot be adjusted by a human mechanism in case of manual control system, or by a controller in case of automatic control system. Whereas what is meant by process variable? Variables we are interested in control, that is they cannot be adjusted manually. The variables we are interested in control, they are called as process variable. Okay, so coming to the input variable, manipulated variable or adjustable variable, and other set of variables are called as disturbance variable. Coming to the output variables, measured variables, they can be measured directly by a sensor or a transducer. Other set of variables are called as unmeasured variables, that is you cannot measure them directly. Okay, coming to the mathematical model, this is a plant which contains a manipulated variable and external disturbances. There are output variables, again measured outputs and unmeasured outputs. Now we are just going to examine how the process reacts with time when there is a change in the manipulated variable as well as when there is a change in the disturbance variable, because these variables are taken as the input variable. The disturbance variables as well as manipulated variables are your input variables to this plant, right? Whereas the measured output and unmeasured outputs are your process variables. Now we are just going to check how the process reacts with the time with the influence of the manipulated variable and the disturbance variable, right? So in order to investigate this, we need to design a controller or a control system. We need to design a controller or a control system. So to design a control system, there are basically two approaches are available. One is called as experimental approach and another one is called as a theoretical approach. I will tell you what is mean by experimental approach. Experimental approach means what we are going to do is deliberately we are going to change the input to the process. Deliberately we are going to change the input to the process, and using recording devices we are going to measure the output. Deliberately we are going to change the input to the process using your sensor or the transducer, measure the output, you just record it. Again I am going to change the input to the process, again record the response, Now suppose if the input magnitude is 1 volt, so now what I am or 50% of the set point. Now I am going to change my input as 60% of the set point, again record the response. So what we are going to do is from the input output responses I am just going to design a controller. But this procedure is effort consuming and time consuming because large number of such experiments must be performed. So what we need is a different approach which is called as a theoretical approach. In the theoretical approach we cannot rely on the physical equipment of the process, whereas in experimental approach we entirely depends on the physical equipment or the practical setup of the equipment, whereas in theoretical approach we cannot rely on the equipment. Instead of that we need a different representation of the process in order to study its dynamic behavior. So this representation is usually given by a set of differential or algebraic equation, By solving this equation, the solution of this equation will yield the behavior of the static as well as the dynamic behavior of the chemical process, right? So this approach is called as your theoretical approach. I hope now you understood the difference between the experimental approach and the theoretical approach. In the experimental approach, the physical equipment of the process is available to us. What we have to do is deliberately we have to change the input, record the output, again change the input, record the output. From the input output responses we have to design a control system. Whereas in theoretical approach, the representation is given by a set of differential as well as algebraic equation. The solution of this equation yields the static as well as dynamic behavior of the chemical process, right? So we prefer this theoretical approach. So this is the need for the mathematical modeling, right? Now we are going to discuss about the mathematical modeling of a level process. In the level process, mathematical modeling of a level process, there are different cases are available. First we are going to discuss about case 1. What is case 1 is when the valve is being linear, when the valve is having linear characteristics. Now you just consider this diagram. There is a single tank system with uniform cross sectional area A, right? So A is the cross sectional area of the tank, R is the flow resistance, Q naught, there is a inlet flow rate Q, there is a outlet flow rate Q naught, right? Now first we must identify the variables involved in this single tank process. This system is called as a single input single output process because we are interested in controlling the level in the tank, right? The variable we are interested in control is the level in the tank. So the level in the tank H is the process variable. By manipulating either inlet flow rate or by manipulating the outlet flow rate, we are going to maintain the level in the tank to the desired value, right? So what is your process variable? The level in the tank is your process variable, whereas the manipulated variable I am just going to consider is the inlet flow rate. The Q of T is the inlet flow rate. By manipulating the inlet flow rate, I am going to maintain the level in the tank H to the desired value. Now, what is the meaning of when the valve is being linear? A resistance that has this linear relationship between the flow and head is referred to as a linear resistance. That is, a time varying volumetric flow Q of a liquid of constant density rho enters the tank, right? So when the resistance is linear, when the valve is linear, you can write the equation as Q naught is equal to H by R. Q naught is equal to H by R. When the valve is linear, R, the hydraulic resistance R is constant. So what will happen is Q naught is directly proportional to H. Q naught is directly proportional to H. Now I am going to obtain the mathematical modeling of this single tank process, right? Single input, single output process. The manipulated variable is the flow in the tank, inlet flow rate in the tank, and the process variable is the level in the tank, right? So I am going to obtain the transfer function. What is meant by transfer function? The Laplace transform of the output variable, that is the process variable, level in the tank H of T, to the Laplace transform of the input variable, that is your manipulated variable, that is your inlet flow rate in the tank. So finally I am going to derive H of S by Q of S using principle of conservation of mass, or in other words using mass balance equation. I am going to derive the equation, right? So what is your principle of conservation of mass? Change in inflow rate minus change in outflow rate is equal to rate of change of accumulation of mass inside the tank, right? Rho is the density. So what is the change in inflow rate? I am going to use a small letters for changes and capital letters for changes and small letters for steady states, right? So what is your changes? Rho into Q of T minus rho into Q naught of T is equal to d by dt of rho AH, right? This is the rate of accumulation of mass inside the tank, that is volume. Rho is the density, volume is area into height, A into H, right? Now neglecting the density rho on both sides, so you will get Q of T minus Q naught of T is equal to d by dt of AH, Now we all know that at steady state there is no changes. What is the meaning of steady state? Inlet flow rate is equal to outlet flow rate. There is no change, right? There is no change. So when there is no change, the level in the tank remains constant, that is H of T is equal to constant. H of T is equal to constant when Q of T is equal to Q naught of T. Okay. Now combining these equations, right, that is equations 1, 2, 3 and 4, you can substitute for Q naught. Q naught is equal to H by R. So Q minus H by R is equal to A into dH by dt. Now I am going to introduce the deviation variables before obtaining the transfer function, right? Initially the process is operating at steady state, so which means that, what is the meaning of steady state? There is no changes, so the inlet flow rate is equal to outlet flow rate, so the level in the tank is constant, so dH by dt is equal to 0. Level in the tank is constant, so the rate of change is equal to 0. Now introducing a deviation variable, so Qs minus Hs by R, S represents your steady state, is equal to 0. Why it is 0? Because there is no change, right? Everything is constant. The level in the tank is maintained constant because inflow rate is equal to outlet flow rate. So dH by dt is equal to 0. Now I am going to substitute equation number 6 into equation number 5. So Q minus Qs is equal to 1 by R H minus Hs plus A into d by dt of H minus Hs. Now I am going to call capital Q as Q minus Qs, capital H as H minus Hs. Now taking Laplace transform and rearranging the equation, now I am going to write the transfer function. What is the meaning of transfer function? Laplace transform of the output variable. What is your output variable? That is your process variable, the level in the tank, divided by the Laplace transform of the input variable. What is your input variable here? The input variable is the inlet flow rate Q of S. So H of S by Q of S is equal to R divided by tau S plus 1, where R is the hydraulic resistance which is constant, tau is the time constant of the system, right? How fast the system reacts. The tau determines how fast the system reacts, right? When the time constant is smaller, the response of the system will be faster and vice versa. Now this kind of system, this single tank system we have considered when the valve is being linear. This is a single input single output system. This kind of systems are called as self-regulating system. I will tell you what is mean by self-regulating system. Self-regulating system, self-regulation process, self-regulation process. What is mean by self-regulation process is for a sustained change in input. What is the meaning of sustained change in input? Suppose if this is my time, now I am going to give a small change in the inlet flow rate. What happens to the level in the tank? Due to this step change, say for example, at steady state the level was at 50%, sorry, the flow was at 50%. Now I am going to change the inlet flow rate from 50% to 60%. Now what happens to the level? Due to this 50% change in the inlet flow rate, the level may be at 11 meter, right? Due to this 10% change, what will happen to the level? It will gradually increase and finally it will reach some final steady state value. This is my H of t versus t. H of t versus t. Due to this 10% change in the inlet flow rate, the level will gradually increase from the steady state value. This 11 meter is your steady state value. So it will gradually increase and finally it may settle into 13 meter or 14 meter, some steady state value. Finally it reaches some steady state value. So this kind of processes are called as self-regulation process. We derived the transfer function as R divided by 1 plus tau s. This R divided by 1 plus tau s is called as first order lag process. First order lag process. First order lag process, or in other words they are called as self-regulation process. That is, for a sustained change in input, the output will reach some final steady state value. It will be within the limit only. Suppose if I change, instead of 60%, I can change my inlet flow rate to 70% or 80%, even 100%. What will happen to the level is, it will reach the subsequent values, maybe 15 meter or 17 meter or 20 meter. Finally, it will reach some steady state value. So this kind of processes are called as self-regulation process, right? Now hope you understood what is meant by self-regulation process. Next we are going to consider the case 2, right? What is case 2 is the liquid level process with the constant outflow. Liquid level process with the constant outflow. What is the difference between your previous diagram and this diagram? In the previous diagram, there was a inlet flow rate, there was a outlet flow rate. The level in the tank is H. Whereas this diagram, if you see this diagram, there is a inlet flow rate, but the outlet flow rate is connected with a constant displacement pump. What is the meaning of constant displacement pump? It will deliver a constant discharge. It will deliver a constant discharge, right? So there will be a inlet flow rate, right? But if you change the inlet flow, let us assume that the process is steady state. What is the meaning of steady state? Inlet flow rate is equal to outlet flow rate. The level in the tank is constant. Again, here also the process variable is the level in the tank, and the process manipulated variable is the inlet flow rate. By manipulating the inlet flow rate, you are going to maintain the level in the tank to a desired value. Now, what will happen? Suppose let us assume that the inlet flow rate is 50% and the outlet flow rate is 50%. The level in the tank is 10 meter. Now, this is called steady state because 50% is equal to 50%. Both inlet and outlet flow rates are constant, equal, right? So the level in the tank is maintained to 10 meter. Now suppose let us assume that I am going to change my inlet flow rate. I am going to change my inlet flow rate from 50% to 60%. 50% to 60%. What will happen to the outlet flow rate? The outlet flow rate will not change from 50% to 60%, right? The level may increase due to the increase in the inlet flow rate. The level may increase. Suppose let us assume that previously it was at 10 meter. Now what will happen? Because of this change in the inlet flow rate, now the outlet level may change from 10 meter to 11 meter or 12 meter. But what happens to the outlet flow rate? The outlet is connected with a constant displacement pump, right? So it will never change. It is always discharge. It will always discharge a constant outlet flow rate, right? Say for example 50%. Even if you change the inlet flow rate from 50 to 60%, the level may increase or decrease depending upon the magnitude of your inlet flow rate, but the output is always constant. The outlet flow rate is always constant, right? So this kind of process are called as integrating process. This kind of process are called as pure capacitive process or integrating process. Integrating pure capacitive process or, once again, this kind of process are called as pure integrator or pure capacitive process. I will tell you why it is called as pure capacitive process. Pure capacitive process will cause severe problems. Why it causes severe problems? Because the tank may run dry or it may get overflow. Because if the inlet flow rate is varied from 50% to 60%, what will happen to the level in the tank? Level in the tank will keep on increasing. Let us assume I am going to change my inlet flow rate again from 60% to 70%. What will happen to the level in the tank? The level will keep on increasing. It will never reaches the final steady state value because the outlet is connected with a constant displacement pump, right? Constant displacement pump. So this kind of process are called as pure capacitive process or integrating process. That is, I am going to give a small step change in the input, right? This is my Q in of T versus a T, small change in the input. But what happens to the level? The level in the tank will keep on increasing and it will never reaches the final steady state value. So this kind of process will cause severe problems. That's what they are called as pure capacitive process or integrating process, and they are difficult to control. Now we are going to obtain the mathematical model for this pure capacitive process or non-self-regulating process. What is the meaning of non-self-regulating process? The output will keep on increasing and it will never reaches the final steady state value. You just see this, it will keep on increasing and it will never reaches the final steady state value. So this kind of process are called as non-self-regulating process. Now we are going to derive the mathematical modeling for this non-self-regulating process. Again, applying the principle of conservation of mass, change in inflow rate minus change in outflow rate is equal to rate of accumulation of mass in the tank. So Q in of T minus Q naught of T is equal to d by dt of rho AH. Again, neglecting the rho on both sides. Now what about the changes? There is a inlet flow rate and there is a outlet flow rate. What happens to the outlet flow rate? The outlet flow rate will never change because it is connected with a constant displacement pump. Remember, it will deliver always a constant discharge. So what happens to the outlet flow rate? The outlet flow rate is 0, right? The outlet flow rate Q naught, change in outlet flow rate is 0. So when you derive the equation, you will get Q is equal to A into dH by dt. Again, the manipulated variable is the inlet flow rate and the level in the tank is your process variable. So taking Laplace transform, rearranging the variables, then you will get H of S by Q of S is equal to 1 by AS. 1 by AS. So now this 1 by S, this 1 by S is called as the Final transfer function is 1 by AS. A is the cross sectional area of the tank, which is constant, right? So this 1 by S is called as pure integrator. Pure integrator or pure capacitive process. Pure integrator or pure capacitive process. What is the problem in the pure capacitive process? Even there is a sustained change in the input, the output will keep on increasing and it will never reaches the final steady state value. So this is the problem with pure capacitive process. So this kind of processes are called as non-self-regulating process, and they are difficult to control. Non-self-regulation process. So when you draw the phasor diagram, when you draw the diagram, phase lag diagram for this self-regulating process as well as non-self-regulating process, what about the self-regulating process? If you give a sustained change in input, the output will gradually increase and finally it will reaches the final steady state value. But what happens in the case of non-self-regulating process? Even if you give a sustained change in the inlet flow rate, the outlet will, the level will keep on increasing and it will never reaches the final steady state value. So if you plot the frequency response, this is your self-regulating process. Self-regulating process. So what happens to the self-regulating process? The phase angle will gradually increase. This is your omega versus phi. What happens to the non-self-regulating process? There is a constant phase lag of minus 90 degree. Why? There is a capacitor or integrator 1 by S is in the transfer function. So there is a constant phase lag of minus 90 degree. This is the difference between your self-regulating process and non-self-regulation process. This is your non-self-regulating process. So they are less stable. Non-self-regulating process are less stable and they are difficult to control when compared with the self-regulating process, right? Now I hope you understood the difference between a self-regulating process and non-self-regulating process, and we derived the mathematical modeling for a self-regulation process when the valve is being linear, and similarly we derived the mathematical modeling for a non-self-regulation process or pure capacitive process. Other cases we will discuss in the forthcoming sessions. Thank you.